Welcome to technical session 5, image and video analysis. I hope everyone is okay, and we are welcome to the authors to present their works here. And we're gonna start with the first working entitled Non-Local Medium Filter for Joint, Gaussian, and Impulsive Image Denoise by Alexandre Levada. Welcome, Alexandre, and let's go.
Hello, everyone. My name is Alexandre Levada, and I'm here to present in this short video a brief overview of the paper Non-Local Medians Filter for Joint Gaussian and Impulsive Image Denoising. So, the main goal of image denoising is the removal of random perturbations in the image while keeping fine details, such as edges, for instance. The main question we want to answer in this paper is this: how to deal with a mixture of two different kinds of noise, additive Gaussian noise and impulsive noise at the same time. So we proposed a non-local medians filter that works by combining two very known filters in the literature that are median and the regular non-local means filter, using both L1 norm and the symmetrized Kullback-Leibler divergence as similarity measures. So the obtained results were promising in the sense that the proposed method performed better for a large sample of images than the individual successive application of median filter and then non-local means filter. To illustrate some results, we have some images here, and from left to right, we have this first column refers to the median filter. We can see that there's a lot of noise, residual noise here in the images. The second column refers to the combination of median filter plus non-local means, regular non-local means filter. We can see that this method is over smooths the regions of the images. And then the third and fourth columns refers to the two variations of the proposed method. As we can see, there is a better trade-off between smoothing and noise removal. So that's the main advantage of the proposed method. Well, for the interest audience, we will talk more about this paper during SIBGRAPI. So this was just a short preview of our work. So thanks for the attention, and that's it.
Hi, Alexandre. Congratulations
Hello.
for the work.
Thank you very much.
Gonna wait for some comments and questions. But before this, I'd like to ask you a question. Does it make sense to think that your method could working on other types of noise? If not, do you have suggestions to modify it to cope with the other image noise?
So let's start. I think the original idea was to deal only with Gaussian and impulsive noises. If we wanna tackle other kinds of noises, I believe it is possible, but we should first try to incorporate a distance measure that takes into account the statistics of that other kinds of noise, because the Kubeck-Leibler divergence, for instance, in this paper, we used the assumption of Gaussian distribution. So when the noise is, for example, is a Poisson noise or other kind of noises, we would have to plug the correct KL divergence for that distribution. So it depends on the statistics of the noise. It is possible to propose these modifications, and we intend to do it in future works, but it is possible.
Very good. Thank you.
Thank you.
So, I don't think that there will be more questions. So I have to thank you again and congratulations for your work. And I'd like to call the next paper. Thank you, Alexandre. So the next paper is Learning-Based End-to-End Video Compression Using Predictive Coding by Matheus, Luiz Henrique, Nilson, Renan, Eduardo Peixoto, Bruno Maquiavello, Edson Hung, Vanessa Testoni, and Pedro Garcia. So congratulations for your work and good luck.
Hello, my name is Matheus Oliveira and I'll be presenting the paper entitled Learning-Based End-to-End Video Compression Using Predictive Coding. So initially, I'll give a quick review on how traditional video codecs work. So given a video sequence, the frames are encoded by two major approaches. The first one is the interframe coding, where only spatial redundancy of the frame is exploited. So the frame is submitted to a transformation followed by a quantization, where the coefficients will be later submitted into an entropy codec. The second approach is the interframe coding. So giving a previously reconstructed frame available to both encoder and decoder, a motion estimation can be applied to the current frame in order to make a prediction for it. Thus, only the difference between the real frame and its prediction needs to be encoded. Usually, this residual is submitted to the same steps adopted in interframe coding. Our main reference for proposing our video codec was the work by Meaning et al. And all its previous versions. So the authors propose an image codec consisting of a variational autoencoder, which is jointly optimized for rate and distortion. The major improvements presented over the versions were focused on the latent probability model. In the cited work, for example, the parameters of the distributions were obtained by an auxiliary variational autoencoder. These works here have an enormous relevance in the image compression field. Now I'm going to present to you our proposed video codec. Our video codec splits the video sequence into groups of pictures. For each of these groups, the first frame is the interframe and all others are interframe, so they need the previous one as reference. Both encoding types, inter and inter, are implemented by two independent autoencoders. However, their architecture are inspired by the cited reference works. So we have an autoencoder here used for inter prediction and an autoencoder here used for inter prediction. Interframe coding is essentially performed by the reference architecture, since this approach handles the frame as an image. However, the architecture had to be adopted for interframe prediction. A target frame is concatenated in channel in channel dimension with its predecessor and reference frame, and then the 6-channel tensor is submitted to the autoencoder right here. So the output of the autoencoder, however, is the input to 2 other networks. So we have here the motion estimation network, which predicts the parameters for warping the reference frame, and the residual network, which aims to predict the residual between the warped reference frame and the target frame. Lastly, the output for both networks are added together and the reconstructed interframe is obtained. It's worth noting here that all blocks and transformation present in the proposed architecture are learned, which leads to an end-to-end approach. Some of the first results obtained by our proposed codec are shown here. Here at first we show some rate distortion curves which refer to the blowing bubbles video from the GVAT dataset. We can see here that our rate distortion curve obtained by our proposed codec is in the same region as the ones obtained by the all intramodes of the newest and traditional video codecs HEVC and VVC. We also provide some visual comparison for an interframe of the basketball drill video. Although our codex uses far more bits for transmitting this information here, a visual comparison allows us to conclude that an end-to-end learned codec can indeed perform the task of video coding. So thank you very much for your attention and have an excellent conference.
Hi, Matheus.
Hi.
Congratulations for your work here again.
Thank you very much.
I have a question for you. I'd like you to call us about how difficult was the train to the duration autoencoder to properly achieve the expected result that you had. Could you give us some comments about this?
Okay, so I don't know if it was clear in this short video, but the networks used for intra and inter codec, they were separated. I mean, they were not like optimized all together. So for making those curves, actually, since they are trained separately, they can be combined. I mean, we can use a specifically trained intra-frame coding with another interframe coding. So we had to make various models for each operation point of our variation autoencoder. So that took a kind of long time. I think we trained 3 intra codec models with about a million iterations and about 5 intercodecs in the same amount of steps.
I imagine. There is a question here by Eduardo. Could the proposed approach hallucinate unwanted details?
That's an excellent question. We didn't see it, but since even the residual is learned how to deal with it, it's a statistical model, so it might happen. Because differently from the traditional video codecs, our residual is not deterministic. I mean, given the output of our prediction, we know the residual is the correct difference between the original frame and the predicted frame. Here we have a prediction even for this residual, so that might happen. I won't say it won't happen for sure, but we haven't seen any of it. That's why I shown this visual comparison to see that the image have a visual pleasing. So
very good. In the graphs that you showed in the first results, you showed a kind of trace of curve, but with it seems that you had so many few points, so just 1, 2, or 3 points that you interpolated to have the specific curve. You have some explanations about that? You have some idea? Because you have so many few points?
Yeah, I think it was just for simplicity, since we had these to train all these models and after run on these videos and to make a comparison with our codex baselines. We had to run all these videos in the traditional dataset, JVAT, HEVC. So I I don't know why. I think that were the points that were in the same region of the baseline. I think it was that, because actually some of the points were kind of out of the that region, because as I said, when we use, for example, uh, an intercodec that was really optimized for quality, but we use as intracodec that will give the first reference frame, an intracodec very optimized for rate, that will lead to a not very good um, result. But that's not because the model can't achieve better results, just because these both codecs, they are dependent on each other, were not trained together. So just to be more, I don't know, just to make a better comparison with our baselines.
Awesome. Thank you again, Mateus, and congratulations for your work
Thank you very
and good
much.
luck
Thank you
in
very
your
much.
future works.
Thanks.
And so we're gonna go to the next paper, which is entitled "Improving Transferability of Domain Adaptation Networks Through Domain Alignment Layers" by Lucas, Daniel, Fábio, João Paulo, and Jurandir.
Hi everyone, my name is Lucas, and alongside Daniel, Fábio, João, and Jurandir, I'll present our work named Improving Transferability of Domain Adaptation Networks Through Domain Alignment Layers. In the last few years, deep learning approaches have obtained a big renown because of their results on many different tasks, for example, on computer vision problems. However, such methods, when deployed to production, tend to suffer to some extent, generally by the problem named the domain shift. This problem is dealt with by the unsupervised domain adaptation research area, which can refer to the single source domain setting or the multi-source domain setting. Most of the current works perform each domain alignment technique at the end of feature extraction process. So in this work, we investigated the effects of the domain alignment on different levels of feature space, aiming to improve the knowledge transferability from the source domain to the target domain. And with this goal in mind, we could contribute in improving the results of state-of-the-art UDA methods, assessing this approach in an extensive set of experiments, and develop a model-agnostic MS-dial insertion algorithm. Roughly speaking, we embedded MS-dial domain alignment technique, which tries to align each domain distribution above a previously defined reference distribution. Particularly, it uses the normal distribution as a reference, allowing the method to be built using one batch normalization layer for each domain. The model expects that the incoming batch must be composed of all observations from all domains, trying to learn feature discriminability from the source predictions and confidence from the target predictions. And to correctly use MS-dial, we must insert them after each convolutional or fully connected layers. However, some CNNs of the UGA methods do not have any batch norm layers. For this kind of method, we developed an algorithm that if there are any batch norm layer in the model, change them to MS-dial. But if there aren't batch norm layers, insert MS-dial immediately after all convolutional and fully connected layers. We access our method into two different tasks: digit recognition with MinIST-M, SVHN, and SINF datasets, and object recognition with offset 31 and offset home datasets. We use the same experimental protocol used by DARN method, which choose one domain as target and use the reminders as source. Repeat 20 times each experiment, assess the performance by accuracy, and present the average accuracy from all runs and its standard error. And first, we run our experiments in their original form, to after perform the insertion algorithm on all methods and run again the experiments. About the digit recognition task, we could see improvements in all methods, especially for M3 SGA, which demonstrated the biggest relative gain of 7%. For the objective recognition task with the Office 31 dataset, we could see consistent improvements in all methods, especially for M3 SGA, which improved the average performance by almost 4%. And for the objective recognition task with the Office 1 dataset, which is more challenging than the others, we could see higher improvements, reaching up to 30.65% for them. And through the investigation of the feature space from the last layer input by a UMAP dimensionality reduction, when inserted our MSDR layers, we can clearly see improvements on class separation, especially in the mini-targeted domain case. And to summarize, we tried to improve the knowledge transferability of the UGM problem setting using the MSDI feature alignment technique on different levels of feature space. And because of that, we could observe improvements up to 30.65% of relative gains. We evaluated our method in an extensive set of experiments, and we also developed an automatic algorithm of MSDI insertion. Here are listed our presentation reference, and with thanks to the grants from FAPESP and CNPq. Finally, thanks for the attention, and if you have any doubts, don't hesitate to contact us. Thanks.
Hi, Lucas. Hi, Benji. Thank you for coming, and very good your work, and congratulations. I'd like to ask you a question. Do you think that the use of generative adversarial networks will bring benefits for your alignment layers?
We try to, we used some data which uses adversarial learning, but all those methods usually tries to make domain alignment just at the end of the process. So yes, as the result shows, some the results can be improved.
Very good. Very good. Do you know the paper called the taxonomy? I think it was the best CVPR paper in 2019.
Taxonomy?
Taxonomy, yes.
No, I didn't see. I'll see later.
Don't worry. The paper talks about transferability, and it was one of the most complete paper in this field. I think you could get or could pinch some ideas from this paper, probably.
Okay.
But I liked so much your work. I think it was a great work, very complex, and very useful because you had a very good improvement of more than 30%. So congratulations.
Thanks.
I don't think you have other questions. So thank you again. I'm gonna go to the next paper. So the next paper is entitled "A System for Visual Analysis of Objects' Behavior in Surveillance Videos" by Sibeli Mara and José Gustavo.
Hello everyone, I'm Sibeli. I'm one of the authors of the article entitled "A System for Visual Analysis of Objects' Behavior in Surveillance Videos," and I will present our work for you. The popularization of CCTV cameras produces a large volume of recording footage, and these materials contain rich content which is useful to comprehend surveillance scene in order to solve crimes or identify suspicious behavior, for example. However, the manual analysis of surveillance videos is an unfeasible task because of their huge volume and long duration. Smart surveillance applications employ several automatic video analysis technologies, including visual analytic strategies, which have been used to improve the video content comprehension. Also, many smart surveillance video analysis tasks focus on detecting and tracking moving objects in the scene. And as these objects are directly involved in the occurrence of strategic events, analyze their behavior may provide a better comprehension of these events. In this work, we focus on some aspects related to the object's behavior, which include presence of objects in scene, relationship and interactions among objects, movement of objects, and scene occupation by these objects. The aim of this work was to develop a system for visual analysis of surveillance videos with focus on the identification and exploration of objects' behavior and their relationship with events occurrence. Here is our analysis workflow. Remember that our system performs a post-event analysis using previously generated video. First, we use the results of a proper tracking method on a surveillance video and we extract all video frames. Then, we generate the layouts from these results. So the user may interact with the layout, executing a variety of exploration tasks. This is the system interface, which contains several coordinated views. The appearance bars view highlighted here by the blue rectangle presents all the identified objects and their presence over the entire video extent. The brush view allows the user to select a region of interest from the scene background. Frame view shows frame from the video highlighting bounding box of identified objects. And the video player view implements a traditional interaction tool used for watching and navigating videos. The system also includes several interaction tools which allow the user to explore meetings and interaction among objects and the object's speed variation. Concluding, the system coordinated views highlight the dynamics and distribution of each object present in scene. The interaction tools provided means to explore several objects' behavior aspects, especially to distinguish between different aspects of interaction among objects, as the number of objects involved in a meeting and the scene regions in which interactions occur. The case studies demonstrated the ability of the system in highlighting objects' actions aspects, such as when an object moves, when an object occupies a certain region of the scene, when the objects interact among themselves, and which objects were involved in these interactions. It allowed to relate these actions to the occurrence of relevant events. Future work included user study with surveillance experts and the adaptation to real-time surveillance scenarios. So we are grateful to CAPS and CNPq for the support in the execution of this work. Thank you all so much for watching and we are ready for your questions.
Hi, Sibeli. Hi, Jose.
Hello.
Thank you for coming. I'd like to double congratulations, Sibeli, for the excellent work and for being a very good representative of the woman in the field. I think this is very good, and I think probably other girls will be inspired by you to research in the field of computer vision. So congratulations.
Thank you.
Yeah. I'd like to know what techniques for object detection and tracking did you use in your video analytical systems? Could you give some ideas of the techniques that you explored in your system?
In the work, we use the annotations from the datasets, and we manually add some annotations to correct some informations about objects bounding boxes. But we tried to use YOLO, but it generated a lot of extra bounding boxes. So we decided to use the annotations from the datasets.
Okay, so YOLO, you use it for object detection.
Yeah, you try to use it.
Okay.
Yeah, just complementing the answer, Luciano. Our initial idea was to use only YOLO or anything related, because as our method does not depend on the object detection technique. I mean, the user can even manually annotate each frame if he or she wants. But of course, we would like to use an automatic procedure for that. But the YOLO proved to be very complicated in defining, in parameterizing in a way that achieves reasonable results in terms of number and persistence of object. It happens a lot that sometimes an object was becoming another object in the video, and it became a mess. So we decided to use previous annotated video to help us to demonstrate the visual layout, because that was the focus of the work, right?
Perfect. Very good. Very good. I don't think we're gonna have more questions. So I'd like to thank you again and congratulations. And I'm gonna go to the next speaker. So the next and the last paper is called the Musical Hyperlapse, a Multimodal Approach to Accelerate First-Person Videos by Diogne, Washington, Luiz, and Erickson.
Hello everyone, my name is Diogne de Matos and this presentation is about our paper titled Musical Hyperlapse, a Multimodal Approach to Accelerate First-Person Videos. This is a joint work with Washington Ramos, Luiz Romagnol, and Erickson Nascimento. With the advance of technology and social media usage, the recording of first-person videos has become a common habit. These videos are usually very long and tiring to watch, bringing the need to speed up them, creating the hyperlapse videos. Despite recent progress of hyperlapse methods, they do not consider inserting background music in the videos, which could make them more enjoyable. One way to combine acoustic and visual content would be to correlate the emotions induced by the video and by the music. Our objective is to speed up a video to the size of a song, combining visual and acoustic contents, also maximizing the video's visual quality. Our contributions are a novel hyperlapse creation method that combines emotions from visual and acoustic contents, and a new dataset comprising diverse first-person videos and songs. Over the past decade, hyperlapse methods have been proposed to reduce the length of long egocentric videos. There are some more classic works focused on optimizing smoothness, stability, and speed up, and there are other newer approaches that also consider semantics as part of optimization. However, none of these works consider the background music content. There are also many works to recognize emotions from music and images. In general, the emotions are numerically represented as points in a plane, where the x-axis is the valence and the y-axis is the arousal. Our method is divided into two main parts: emotion curves creation and optimal path selection. First, we use neural networks to create the video and music emotion curves. For the video, we use a patterned convolutional neural network topped with a fully connected network to classify each image as a point in the Valens-Arousal plane. For the song, we use a feature extractor also topped with a fully connected network to classify each song segment as a point in the Valens-Arousal plane. Then, we use an optimization algorithm to find the best subset of frames that maximizes the emotion curve's similarity and the video's visual quality. We create three two-dimensional cost matrices and a three-dimensional cost matrix in which finding a minimal cost path gives us the best subset of frames for the output video. To run the experiments, we created a dataset with 8 egocentric videos with various lengths and contents, and 5 songs with different styles and emotions. We evaluated our method considering 4 metrics: the emotion similarity, the speed-up ratio, the FID score, and the shaking ratio, and compared our method with 2 other hyperlapse creation methods, the Microsoft Hyperlapse and the Sparse Adaptive Sampling. Our method obtained the best results for the emotion similarity and for the speed-up ratio. For the FID score, Sparse Adaptive Sampling got the best results, and for the video shaking ratio, the results were very similar. Here, we show a qualitative comparison with a baseline. On the top, we show the output video. On the bottom, we show the valence curves, the arousal curves, and the similarity curves. We also show the similarity intensity in the Valens-Arousal plane. The greater the red intensity, the greater the similarity. Note that in several parts, our method maximizes the similarity between video and the audio curves. Also note that our method obtained greater similarity. In this work, we presented a new algorithm for creating hyperlapses, which combines the emotions induced by video and music. We showed that our method maximizes the emotion curve similarity without losing significant visual quality. For filter works, we can improve the emotion classifications and similarity mastering and run the experiments with more videos and longer videos. That is all. Thank you for watching.
Hi, Jogney.
Hello.
Coming.
Thank you too.
I think this last work closed the session with a very high quality of the work. So congratulations for
Thank
your
you.
work. I have a question for you. Since to measure the emotion is kind of a subjective task, so each one can evaluate the emotion of the video as a very personal point of view. So do you think that the protocol you use it to evaluate your work is able to capture the subjectiveness of the task to evaluate the emotion?
Yes, our method can we work with the main values of the labels of the dataset for the music emotion recognition and for the video emotion recognition. For example, for the music, each song segment was rotulated by a lot of persons. For example, 10 persons rotulated the music. Then we took the main value of the 10 persons. However, we can also work separately with each one of the labels. Also for the music and for the video. Okay.
But did you consider the bias? Did you consider the bias of the annotators? And you are considering to evaluate these bias in the future?
No, no, because we are focused on the main user. We do not focus on the bias. We perform a filtering when the outliers was removed, and we focus on the mean values for the tasks.
Okay, very good. Also,
But our work also we can also reach a single change on the emotion recognition blocks of our method. We can change to consider the bias.
awesome. Eduardo Gastal is saying that it was a nice work, and if you could, if a user provide, could you, if a user could provide manual constraints for video music alignment.
Well, our method, our algorithm, in our algorithm, we only we fixed the content of the video. We do not put the option of the user changes the constraints. Then if you get our algorithm, you will be not able to change the constraints. You only can select the music that you want to put in the video and the video. Then the entire constraints are selected by the algorithm. You do not change any configuration in our method.
But would it be interesting to provide some user constraint to modify your algorithm to have different types of results at the end?
Yes, that's old school. Old school
It'd be nice. It should
interesting.
be easy. It should be easy to
Yes,
modify
yes.
your algorithm. Very interesting. So, Jogney, so far so good. We don't have any more questions so far. So, thank you again. Congratulations for
Thank you too.
working.
Thank you.
And since this is the last work, I'd like to thank you everyone for watching this session. And you're gonna continue the conversation at the Discord channel. You can see this the name of the channel in this slide. So what is coming next is the keynote Regine Gilbert at 3 o'clock, and you could check this on the SIBGRAPI program. So thank you everyone, and have a nice afternoon for everyone.